Hello everyone and welcome back to another calculus video. In this video we are going to talk about infinite series. So we had talked about sequences before where we have a list of numbers that follow some kind of pattern. So maybe we have a pattern um, a sub n could be something like 2 to the n over n squared. And we could list out a set number of terms. So maybe we're looking at just a1, and that would be 2 to the first over 1 squared, which would be 2. Or a2 would be 2 squared over 2 squared, which is 1. Or even a3. So we're listing the terms here of the sequence. This would be 2 cubed over 3 squared, which would be 8 over 9. With an infinite series, now we're looking at the sum of an infinite number of terms. So we could write this way, the sum from n equals 1 to infinity of 2 to the n over n squared. And that Greek letter sigma means we're adding all these terms together. So when I plug in 1, I'm going to get that number 2 plus, and then when I plug in 2, we ended up with 2 squared over 2 squared, which is 1. And then when I plugged in 3, I would end up with that 2 cubed over 3 squared, which is 8 over 9. So we would add these things together. And now we're going to start asking the question, what happens when I add an infinite number of terms together? Do I end up with something that converges to a particular value, or do I end up with something that diverges and goes off maybe to infinity or negative infinity? And that's what we're going to spend the rest of the chapter analyzing. So we're building small. We started with sequences. Now we're talking about series, and then we're going to build up to all the different tests we can use to test whether a series converges or diverges. But before we jump into the test, let's look at series a little bit more. So for each of the following series, let's use this sequence of partial sums to determine whether the series is going to converge or diverge. That first one, we're looking at the sum from n equals 1 to infinity of n over n plus 1. So let's look at some partial sums. And we're going to use this I'm going to use a capital cursive S. So this notation in the curly brackets to talk about these partial sums. So this is part A. So if I plug in 1, then I'm going to end up with 1 over 1 plus 1, which is 1 over 2. So that's the partial sum for just the first term. If I'm looking at 2, I want that first value, which is going to happen at n equals 1. So when I plug 1 in, we get 1 half. And then I'm going to plug 2 in. So I'm going to have 2 over 2 plus 1, which is 3. And then now let's look at the third partial sum. So this notation means the third partial sum. So we're going to plug in 1, we're going to plug in 2, and then we're going to plug in 3. And we're asking, what's happening to all these values? When I plug in 1, I'm going to get 1 half. When I plug in 2, I'm going to get 2 thirds. And when I plug 3, I'm going to get 3 over 3 plus 1, which is 4. And then we'll look at that fourth partial sum. So we're plugging in 1, 2, 3, and 4. When we plug in 1, we get a half. When we plug in 2, we get 2 thirds. When we plug 3, we get 3 fourths. And when we plug a 4 in, we're going to get 4 over 5. So that first term was a half. That second sum was a half plus 2 thirds. So I'm adding something that's bigger than a half here. So this guy is bigger than a half plus what I started with was a half. Same thing here. I've got a half plus 2 thirds, which is bigger than a half. Oops. Plus 3 fourths, which is also bigger than a half. And then same thing here. I'm always adding something that's bigger than a half. So we could think about that second partial sum as when I compared it to 1/2 plus 1/2, 2 times a half. I could compare that third partial sum to 3 times a half, and that fourth one to 4 times a half. You can see how it's getting larger and larger and larger and larger. So this guy is going to diverge because we're adding things that just keep getting bigger and bigger and bigger. We started with a half, we added a half plus 2/3, and 2/3 is bigger than a half. And then the next partial sum, the third one, was also adding something bigger than 1/2. So I'm adding something that's getting larger and larger, so you can see how that thing is diverging. I'm going to pull up Excel so we can play with that one just a little bit more. So I'm going to have a column for n here. Call this n equals. And then this is going to be my equation. So we're looking at the sum n equals 1 to infinity of n divided by n plus 1. Let's see if I can move that right there. So let me fix my formula here. So I'm adding 1 each time. So I'm going to let this column represent the terms of the sequence. So this will be equal to n divided by n plus 1. So when I plug in a 1, I'm going to get 2, oh, 1/2, excuse me. When I plug in 2, I'm going to get that 2/3. And this is going to be my sum. This is the sum. So it will be equal to this plus this. Oops. You can see how everything's growing. All those terms are growing. So if I were just to copy this down, there's no end in sight for this. More terms I have, the larger everything gets. So you can see how those sums are growing without bound. So we say that that sum's going to diverge. Now let's look at B. We're looking at the sum from n equals 1 to infinity of -1 to the n. If we think about what's happening with that sequence, those terms are bouncing back and forth between -1 and +1. So if I look at that first partial sum, it's going to be -1 to the first, which is -1. The second partial sum would be -1 to the first plus -1 squared, which is -1 plus 1. So you see how my terms are bouncing back and forth between negative and positive? So then when I start adding them together, in this case, I'm going to get 0. But look at what happens with that third one. We've got -1 to the first plus -1 squared plus -1 to the third. So I'm going to have -1 plus 1 minus 1, and that's going to be a -1. And then when I look at S4, -1 to the first plus -1 squared plus 1 cubed plus negative 1 to the fourth, I'm going to end up with negative 1 plus 1 minus 1 plus 1, which is going to give me 0. So while the terms are bouncing back and forth between negative 1 and 1, that sum is bouncing back and forth between negative 1 and 0. So if we're adding an infinite number of terms together, and the question becomes, well, where am I stopping? Am I stopping on an even or am I stopping on an odd? Because I'm either going to get 0 and 1. Well, if I'm adding an infinite number, I'm not stopping. So I'm always bouncing back and forth between those two sums, which means this diverges. And then let's look at part C. If we look at S1, we're going to have 1 over 1 plus, sorry, 1 times 1 plus 1, which is 1 times 2. So there's my 1/2. If I look at S2, so when I plug in 1, I'm going to get 1 over 1 times 2. And when I plug in 2, I have 1 over 2 times 3, which is 1/2 plus a 6. If I look at that partial sum for 3, I'm looking at the first 3 terms. So I'm going to have 1 over 1 times 2, so that's n equals 1. N equals 2, and this is going to be 1 over 2 times 3. And then at n equals 3, I'm going to have 3 times 4. So I'm going to have 1/2 plus a 6 plus a 12th. So you can see how what I'm adding is getting smaller, which is different than what happened in the first one, where when I was adding something, I was getting larger and larger. And we'll look at S4. So this is going to be 1/2 plus a 6 plus a 12th, just following those first 3 terms. And then now when I plug in 4, I'm going to have 1 over 4 times 5. So that's going to be 1/2 plus a 6 plus a 12th plus 1/20th. And we could plug these in the calculator to get a decimal representation. So this is 1/2, right? If I have 1/2 plus 1/6, that's 2/3. So 0.6 repeating or 0.67. If I have 1/2 plus a 6 plus a 12th for that third partial sum, that's going to be 0.75. Oops. Let me give myself a little space to write here. There we go. So 0.75. And that fourth partial sum, 1/2 plus a 6 plus a 12th plus a 20th is 4/5, which is 0.8. So you can see how everything looks like it's starting to level off. So to me, it looks like this is possibly going to converge. So let's go back to our Excel sheet. So now we're looking at a different formula here. This is going to be 1 over n times n plus 1. So I'm going to change my formula here. So this is 1 divided by n times. Excel lets you to type in the times. And n plus 1 needs to go in parentheses. Oops. Plus 1. So there's that first term. I'm going to copy my formula down, and I'm going to go through all of my rows here. So you can see how we're adding. The subsequent terms are getting smaller and smaller and smaller. And check out what happened in that last column. That's the sum of everything. So if I add all those terms together, here's my second partial sum. You get that 2/3, which is 0.67 rounded. Here's the third partial sum and the fourth partial sum. You can see how everything is, it looks like it's converging to about 1. So we would say part C converges. So let's look at another one. This one's called the harmonic series. We're looking at the sum from n equals 1 to infinity of 1 over n. And this one's a little surprising. I'm looking at plugging in the value. So when I plug in 1, I'm going to get 1 over 1, which is 1. That's my n equals 1 term. When I plug in 2, I'm going to get 1 over 2, which is a half. And when I plug 3, I'm going to get 1 over 3, which is a third. And then when I plug in 4, I'm going to get 1 over 4. So we are adding things that are smaller each time. So you would think this one converges, but this one actually doesn't. It actually diverges, and it diverges very, 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 very slowly. So if we were to plug this in the Excel, let's say we looked at the first 10 terms, then we could find that partial sum and we would get about 2.9. If we looked at the first 100 terms, everything is going to grow slightly, but it's going to grow really slowly because you're always adding something super small to it. So this is going to um, go to about 5.19. The first 1,000 terms goes to about 7.49. So it's growing, but it's growing at a really slow rate because we're adding something so small. And so then the question becomes, well, how did I know this guy was going to converge and this one's going to diverge? Well, like I said, we're going to lead into some tests to help us determine what's happening with those. But the harmonic series, this is one that I would memorize. The harmonic series is always going to diverge. It's a very, very slow divergence. You can see from this table that the first million terms only adds up to 14. So let's look at some properties. We have, let's say we have two sequences and we know that they are convergent. Sorry, series, not sequences. We have, and we're going to look at the sum from n equals 1 to infinity of each of those. We'll call them a sub n and b sub n. If I want to add these two together, okay, and I know that they're both convergent series, then I could think about, because you're starting at the same place, rewriting this as a sum of one series. Same thing with subtraction. If I'm subtracting each one, so the sum from n equals 1 to infinity of a sub n minus the sum from n equals 1 to infinity of b sub n, I could rewrite that as one summation as a sum from n equals 1 to infinity of a sub n minus b sub n. And then we have a constant multiple rule where we could think about pulling that constant out. Because if we were to write this out and expand it, every term would have that constant value c. So for any real number c, the series, the sum from n equals 1 to infinity of c times a sub n converges. And that's because a sub n is a convergent series. And I could rewrite that as c times the sum from n equals 1 to infinity of a sub n. So let's look at example 2. Example 2 wants us to use algebraic properties of convergence series. So we're going to evaluate this. This is a sum from n equals 1 to infinity of 3 over n times n plus 1 plus 1/2 to the n minus 2. So we're going to look at some things that we know. So let's talk about what we know. I put my computer in tablet mode. What do we know? We know the sum of 1 over n times n plus 1 as n goes from 1 to infinity goes to 1. We talked about that a little bit ago. And I'm going to tell you that the sum from n equals 1 to infinity of 1/2 to the n minus 1 is going to go to 2. Now, we haven't proven this, but we could use our Excel spreadsheet and we would see that. So if we know these things, then let's apply properties. So I'm going to start by rewriting this as two different sums. So I'm going to have the sum of 3 over n times n plus 1 plus the sum of 1/2 n minus 2. Now I could think about pulling that 3 out of the first one. So 3 times the sum of 1 over n times n plus 1. And I know what this guy is. That guy's going to be 1. Question is, how am I going to be able to manipulate this guy? What if I were to rewrite that second sum as negative 1/2 to the n minus 1 minus 1? N minus 1 minus 1 is the same thing as the exponent n minus 2. And I could think about n minus, well, let me fix that. Think about this as n minus 1/2 to the n minus 1 times 1/2 to the negative 1. Okay, so if I multiply and I have the same base, I would add the exponents together, and that's the same exponent that I started with. And I'm going to pull that 1/2 to the negative 1 out. We'll simplify it in just a minute. And that's going to leave me with the sum of 1/2 to the n minus 1. And then now we can use what we know. So this is going to be 3. And we know this sum from n equals 1 to infinity of 1 over n times n plus 1 is 1. We showed that one in Excel. Plus 1/2 to the negative 1, which is really 2. And then that sum from n equals 1 to infinity of 1/2 to the n minus 1 is going to go to 2. And that's going to give me 3 times 1 plus 2 times 2. 2 times 2 is 4. So we're going to get 7 for that sum. So the key is rewriting it in terms of things that we know. That's going to lead us into this idea of a geometric series. So a geometric series is something that we could write in the form of a times r to the n minus 1 when the sum is from 1 to infinity. Some textbooks will write this from n equals 0 to infinity. So if I move this n equals 1 back 1, then to produce the same terms, I would have this r to the n power. So that's going to produce, when I plug in 0, this is going to be a times r to the 0 plus a times r to the 1 plus a times r squared, and so on. You can see how that's producing the same terms. So depending on the book, you may see this starting at 0 or at 1. Either way, it's going to work the same way. If that r, I'll call that the ratio, is something that's between negative 1 and 1, so we could say that absolute value of that r value is less than 1, then it's going to converge always. But if this is larger than 1, the absolute value of r is larger than 1, then it's going to diverge. So that's how I knew this guy was going to converge, because this is actually a geometric series. With a geometric series, we can find the sum of it quite easily. If we know it's convergent, then that sum from n equals 1 to infinity of a r to the n minus 1, or we could write it from n equals 0 to infinity of a r to the n. That sum is going to go to a over 1 minus r. So if I go back to my series up here, the sum from n equals 1 to infinity of 1/2 to the n minus 1. So if I wanted to show that sum, it's a over 1 minus r. So I have an understood 1 in front of that 1/2. So that's my a. And my ratio is 1/2. So I'm going to have 1 over 1 minus a half, which is 1 over a half, which is going to be 2. So that's where that 2 came from, was recognizing that that was a geometric series. And we would see that if we used Excel also. So let's look at example 3. We want to determine whether each of the following geometric series converges or diverges. And if it converges, we want to find the sum. The first one is a sum from n equals 1 to infinity of -3 to the n plus 1 over 4 to the n minus 1. Our goal is to rewrite this as a geometric series. So we want to rewrite this as the sum from n equals 1 to infinity of a r to the n minus 1. So I've got an n minus 1 on that 4, but I need to rewrite that -3 as an n minus 1. So let's see if we can rewrite some things. So what if I were to rewrite this as -3, and then this would be -3 to the n over 4 to the n minus 1. So I kind of thought about pulling out a -3 from that -3 to the n minus 1. And now I'm going to do the same thing again, and then now I'm going to be left with -3 to the n minus 1. So if you think about multiplying, and you have the same base, you would add the exponents together. So we're going to have a 1 plus a 1 plus n minus 1, which gives me that n plus 1 there. And now I can combine some things. -3 times a -3 is 9. And then I have -3 to the n minus 1 over 4 to the n minus 1, which is -3 over 4 to the n minus 1. So now I've got it written in proper form. We know this thing is going to converge. It converges because my absolute value of r is less than 1. My absolute value of r would be the absolute value of -3/4, and that is less than 1. So then what would the sum be? The sum is going to be a over 1 minus r. So in this case, my a is 9, and my r is -3/4. So I have 9 over 1 plus 3/4. 1 plus 3/4 is 7/4. Keep change flip. 9 divided by 7/4 is 9 times 4/7. So that sum is going to be 36 over 7. Clean up my notation. This is a 9 in the numerator, and then this is the letter A. So A over 1 minus R. So now let's look at B. We're looking at the sum from n equals 1 to infinity of e to the 2n. We need to rewrite it. So we need that exponent to be n minus 1. So I'm going to rewrite e to the 2n. I'm going to think about it as let's try e squared to the n. We know when we multiply, we know when we have a power to a power, we multiply the power. So that's the same thing as that 2n I need this to be an n minus 1. So what if I were to rewrite this e squared to the n? Let's change it to n minus 1 and multiply by e squared. Let's see if that works. So this would be, if I were to multiply this out, power to a power, we multiply the power. So this would be 2 n minus 1. And then when we multiply and we have the same base, we would add the exponents together. So we would have 2n minus 2 plus 2, which gives me that 2n exponent that I wanted. So there's my rewrite. So we can see that, let me rewrite this a little bit better. So we have e squared. So there's my a. My r is e squared also. And we can see that that r value is greater than 1. So this is going to diverge. If it diverges, then that means that the sum is not going to a specific value. It's shooting off to infinity. So in this next example, we're talking about how we can write repeating decimals as fractions of integers. So what fraction would we need to get the repeating decimal 0.26262626? And specifically for this one, we want 3.26262626. So there's two ways to do this. We could think about this as a geometric series, or we can think about this in a slightly different way. I actually like that different way better. I'm going to start by showing you the geometric series. So if we've got 3.26 repeating, that's 3.26262626 forever and ever and ever. So what are we adding to get to that? Well, we're adding 3. So that's where that number from the decimal is coming from. That 0.26, that first 26 group, we could write as 26 over 100. That next group would be 26 over 10,000. And then that third group would be 26. And I'm going to add 2 more zeros. Which would be 26 over 1 million. So notice I'm taking that repeating piece and I'm putting it over its place value. So this is that last 6 for that first group is in the 100th place value. That the last 6 in the second group is in the 10,000th place value. And then that last 6 here in that third group is in the millionth place value. So the question becomes, how could I write that? Well, this is going to be 3 plus 26 over 10 squared plus 26 over 10 to the 4th plus 26 over 10 to the 6th. So this is going to be 3 plus some kind of sum from n equals 1 to infinity. Remember, we're trying to write this as a geometric, so 1 to infinity of a times r to the n minus. So what if we use 26 over 10 squared as my a, and my r is 1 over 10 squared. Let's see if that produces it. So we're going to try it. If I plug in 1, I'm going to have 26 over 10 squared. And this would be times 1 over 10 squared to the 0. If I plug in 2, I'm going to have 26 over 10 squared times 1 over 10 squared to the 2 minus 1, which is 1. And that multiplies together to get 26 over 10 to the 4th. So this is my series. And so the sum is going to be 3 plus whatever that sum of that geometric series is. And we know that's a over 1 minus r. So my a is 26 over 10 squared over 1 minus r, which is 1 minus 1 over 10 squared. So I have 26 over 10 squared over 99 over 10 squared, which is going to be 26 over 99. So if I have 3 plus 26 over 99, which is 323 over 99, then that's going to produce that 3.26262626. So this is option A. I like option B. I think it's more intuitive. So we've got this number 3.2626262626, right? So what if I were to multiply this? Let's call it B. And that decimal repeats until infinity. If I were to multiply this by 100, so that the decimals line up, if I move this 3.2626 by multiply it by 100, I'm going to get 326.26262626 forever and ever and ever. And if I were to subtract all those decimals forever and ever and ever and ever, do you see how those decimals would just cancel right out forever? So I have b minus 100b, which is minus 99b, and then 3.2626 minus, put brackets around that, minus 326.26262626. The decimals are going to cancel. 3 minus 326 is 323. And then if I divide everything by that negative 99, then b is going to be 323 divided by 99. So both ways will give you the same answer. I think writing it as a geometric series is a lot more work, so I like option B. There's your fun. So let's do another one just for fun. Let's say we have 2.8 repeating. And we want to write that as a decimal. So I'm going to use option B to do that. So I'm going to call B 2.8 repeating. And then this time, I don't need to multiply by 100. I can multiply by 10. Because if I multiply by 10, those decimals are going to line up. And when I subtract, they're just going to cancel right out. So B minus 10B is a minus 9B. And then 2.8 repeating minus 28.8 repeating. You see all those decimals would cancel right out. And 2 minus 28 is a minus 26. So B would be 26 over 9. So what you multiply by really depends on that decimal repeat. We multiplied by 100 in the first one because I wanted those decimals to line up. If I multiplied this guy by 10, then I would have had a 6 as that first number after the decimal, and when I subtract, they would not cancel out. So that was the difference there. We're going to look at one more series, and this is a telescoping series. We want to determine if a telescoping series is going to converge or diverge. So this is where we're going to expand, and we're going to look for patterns when we expand, see if some things are going to cancel. So if we were to plug in 1, n equals 1, we're going to have cosine of 1 over 1, which is this 1, minus cosine of 1 over 1 plus 1, which is 1 over 2. So there's what happens when I get n equals 1, plus, and then I'm going to plug in n equals 2. So this is going to be cosine of a half minus cosine of a third. And then I'm going to plug in 3. So this is going to be cosine of a third minus cosine of a fourth. So if we were to look at these, you can see how those cosines of a halves, cosines of a thirds are canceling, cosines of fourths, and so on. And we're going to go down towards the end if we were to look at the nth or the kth partial sum. So let's go down to n equals, I'll call it capital N. So this would be cosine of 1 over n minus cosine of 1 over n plus 1. And then let's go back one and see if we see a pattern here. So if I plug in n minus 1, this would be cosine of 1 over n minus 1 minus cosine of 1 over n minus 1 plus 1, plugging n minus 1 in there for that n. And do we see any kind of patterns? So we said up front that the cosines of 1/2 are going to cancel, and 1/3 are going to cancel. That means the 1/4 are going to cancel, and so on. And you can see how these are going to cancel. And if we were to go back another to n minus 2, we're going to see that cosine of 1 over n minus 1 cancel. So everything is canceling out except the first term and the very last term for our sequence. So in general, what's happening is that kth sequence value, or we'll call it the nth sequence value, is going to be cosine of 1 minus cosine of 1 over n plus 1. So now we're going to take the limit. So we're going to take the limit as n goes to infinity of s sub n. For us, we want to know what's happening. So we have cosine of 1 minus cosine of 1 over n plus 1. So as n goes to 1, cosine of 1 is going to 1. This is going to cosine of 1 minus, and then if n gets larger and larger, then the cosine of 1 over n plus 1 is going to approach cosine of 0, which we know is. So this is going to approach cosine of 1 minus 1. And if we were to plug that into the calculator, we would get about negative 0.46 for that. So there's a telescoping sequence. With a telescoping sequence, we're looking for patterns. We're expanding it out to determine what's going on. Are there any things that can cancel? And there are some things in the middle that cancels with this one. With this one, we're only left with the first and the last terms. So then we take the limit of that partial sum to get what that value is going to be. So this guy does converge. And then its sum is cosine of 1 minus 1, which is about negative 0.46.